All right, so yeah, I had a little fun with this title when I originally submitted. I was just thinking of different words that were associating with some concepts I was playing around with, and I sort of strung them together, kind of in a possibly gimmicky way, but there are some interesting reasons I picked these specific three words. So there we go. So first of all, before I go into each of the words, I want to kind of touch on a overarching theme here. Sorry. I want to talk about the fact that Erlang makes trade-offs, and we all know this really well. It's not the fastest language. It's not the most safe language. It's not even the most dynamic language in many senses. It's not the most scalable language, depending on what you're doing. We're still working on, the many core world, and there are tools that maybe trump Erlang in doing that in some areas. But Erlang is very deliberate with every single trade-off it makes, and all of these capabilities build a really rich environment. And every time we use Erlang, all of those things are at our fingertips. And if we're not really orienting ourselves to take advantage of all of these things, it just goes to waste. And we're just wasting all of these great features. And I'll be going over one of them today specifically. So live, don't worry, this doesn't mean live coding. I thought of doing one live experiment where the failure of the experiment was actually the point, so that way demo gods could not fail me. I would just crash a node by showing how tracing can go out of hand. But live means all of these sorts of topics I'm going to talk about are live systems and things where you're not necessarily running them in a harness, you're actually touching live real code paths, stuff that you would actually run in production, even if it's during development. Distributed is important. Everything you do in Erlang is somewhat distributed in this process sense, but there are also the dist-url components to consider, and this is a really interesting point where problems come up and where limitations of sort of easy ways of thinking break down, and we can talk about why that's a problem with tracing. And spying. The interesting thing about this word is that we can do a lot of instrumentation, and there were some really great talks on instrumentation. But the problem with a lot of that is it's sort of forward-thinking instrumentation, where you need to place something in your code, like a log statement or some sort of code that emits some metric to another system that can be collected, or some sort of point that can be configured explicitly to give you behavior you want. The specific intent here is to take Erlang code and somewhat spy on it. Without the Erlang code needing to adjust itself to your needs at that point in time, you can extract very rich information out of the system. Even while writing this talk, I was surprised by some things I didn't even know I had access to get. Hopefully I'll be able to share some of those. Now, when I first submitted this talk, I was also working on this little experimental tool, clouding. It was a tool that was sort of born out of this idea of using tracing to enhance some of our testing of our system, as well as troubleshooting of similar problems in production. There were some really interesting similarities between the two. And I'll talk more about the similarities that you start hitting when you're doing types of development in Erlang and operations in Erlang. And it's a really unique thing, I think, to the Erlang and OTP system. But yeah, so I submitted the talk. Brilliant. I will work on it and then hopefully show what I built at the end. So So the next step was I had this first prototype. I call this the fancy toaster, but really it was like, okay, I have this specific problem and I have a really slick way of solving it. And it was basically a way to extract this information automatically using little declarative terms. So they were kind of like properties. If you've ever used property-based testing, you'd be able to say, I expect these things to be called, and with the arguments, I expect this model to hold for what you observe. And it worked in a couple cases, but it was really, really easy to break. One problem with that is you don't always have very clear one thing in, one thing out patterns in your code. You could have one thing in and 1,000 things out, and deciding when you have enough of those things to make a choice, or specifically which ones to ignore in some cases, became harder and harder. So I started thinking more about this actual prototype and said, well, maybe I can adjust it. Maybe I just need something simpler, and then I can tell the system a little more about what I want specifically, rather than leaving it so automatic that it feels magic. So that was prototype 2. Okay, fine, I won't build the toaster, but I'll make it really, really easy to get what I need out of this. And this prototype was fine, but the issue here is it wasn't much better than just a couple extra handy functions here or there on top of otherwise standard Erlang features. And the big things ended up being mostly things like safety features. If you're in production, the last thing you want to do is overload the system just because you were curious about what type of data was being passed into some function. And that I've done a couple of times, fortunately not in any completely earth-shattering ways, but I've definitely crashed nodes doing this. So this was a learning process of sort of how to do it safely, but it didn't necessarily feel like it was moving the ball forward for me. So I kind of went back to the concept. So prototype 3, I started thinking more about what the different parts were that I was dealing with. What if this bigger problem of doing all of this work, set up and tear down and gathering of information and the analysis, wasn't actually one problem. It was a series of problems, and that what I really didn't want was this one simple thing. I actually wanted something completely different, and what I could have done was build a series of simpler tools. So the context for this whole process of prototyping is worthwhile to know, because it's an interesting way to think about the differences between developing and using some of these features of Erlang versus other languages. So I work at a company called Cloudant, and basically every single employee, without exception, is involved in the day-to-day running of the business. Now, for some people, this means they're on support. They'll be answering emails. But for much of the engineering team, unless they're actively developing something, they're doing operations work. And this operations work is basically, the direct equivalent of, making sure things are running smoothly. And if your code that you applied last week has issues, then you're going to pay the price. If someone else's code does the same, you're going to pay the price. And so the way the team dynamic works, the way your own code review works, the way you feel about developing changes, and it pushes a lot of different pressures on your development that wouldn't otherwise exist. So this sort of responsibility pushes you to start reevaluating what's okay, because you're not just sort of going through an iteration, releasing a product, and then doing some QA, and then getting a bug report back. You're literally responsible for it actually working, and you will be up late if it doesn't. You'll get paged when you don't want to if it doesn't. This sort of thing brings a lot of creativity to the table. There's a lot of room for, I guess I would call it, change in your natural trade-off as a developer if that's where you're starting. Or if you're an operator and you do some of the development, that changes as well. You start understanding why there are limitations with how things are actually run and what can be done to simplify that. So maybe a better title for this talk would be one of these, being a creative operator, or you'll never develop the same way again, which is very true after a few months at Cloud and even today. So I'm not going to go over all of these other things. These are things that I could easily talk about in the same context. There were great talks. Brian's talk yesterday morning on instrumentation at Adderall was great. Really shows the value of having information so you can make decisions. Very often you have a lot of that information, but you need more, and we'll talk about where some of these things come in. During testing, how you do testing in Erlang, it's really tough to know ahead of time what's going to work and what's not. There were talks on property-based testing and those sorts of things. I'm not going to go into that either. And best practices, ideas on how to actually roll your releases, or all of those sorts of things are out of scope as well. So this is all about tracing. So a couple quick asides, because some people might disagree with some things I say. This is not necessarily saying you shouldn't be using certain preventative mechanisms and focusing on those when you can. Your unit tests and hopefully even property-based tests are a huge, huge benefit. But likewise, there's a lot of code that just doesn't fit well into that. If it's not a state machine and if it's not a pure function, a property-based test isn't necessarily going to be easy to write, or even write correctly. And you may find that you have something that you think covers what you want, but doesn't actually generate all of the cases that could be problematic in production. Likewise, there are lots of ways those things slow you down at the wrong points in time. I do believe that a lot of organizations need to invest in their tooling and basically know where they're going and be smart enough to stay the course and say, okay, this is going to hurt now and we'll get there. But if we take a shortcut and don't invest in this kind of test or this kind of coding practice, then it will hurt us down the road. That's great, but also, businesses live and die, and you need to release a product sometimes. So there's going to be a balance to strike. So the other part to this is it's okay to be dynamic. It's okay to not be formally verified. It's okay to actually not be sure how things will work in every single case, as long as you know what your course is going to be and what that's going to affect. So Erlang, which is really mostly Beam and OTP with some syntax. So I don't know how many people here have actually started, as a developer in Erlang, just reading the source code. I highly recommend this. It's not necessarily easy to go through some of this code. Some of it's really old, so sometimes that's a little painful to go through. Some of it's C code. That is much harder, and it's portable C code. So in terms of portability, you're going to have a lot of if-defs in there, and you're going to have to sort of figure out what code is actually being run in some cases, and that can be really challenging. But it's worthwhile doing because you see a lot of ideas, and you see the use of a lot of things that you wouldn't know otherwise existed, and techniques that seem to just sort of be lost or implicit and implied and not really shown anywhere in the documentation. So yeah, fortunately a lot of Erlang is in Erlang, so leveraging this code base is sort of an example, a pool of things you can learn from is really beneficial. I also recommend looking at what things compile to. There's core Erlang, there's the Beam code that is actually generated, and there's the actual bytecode that's run below that if you really want to see that as well. These are interesting to look at, and they're part of how I would recommend discovering things like Erlang Trace. Now, the Erlang Trace API is more than just this call, but if we look at Trace 3, I'm just going to go ahead and click through on this. I think it should open a tab. Is it opening? Here, I'll just do this. Okay, I'm not online, so I guess I won't show this. Actually, maybe if I drag this over here. This is a cool program called Dash. And I've got offline copies of lots of different sorts of documentation. So Erlang, and we can go to Trace here. I just wanted to show this. We'll kind of go over some of this, but it's got a lot of things to go through, a lot of different things you can be aware of. Call is probably the most common thing people think about when tracing is said, but we've got returns, we've got exiting and running, so if you want to know when something's scheduled and in what order things are being scheduled, running is amazing because you can basically get exactly that information. We'll talk about the caveats with that. Garbage collection, it's actually really great to be able to start measuring and saying, oh yeah, we've got a lot of garbage over here. I'm curious how much it's actually cleaning up versus holding. Maybe I've got a leak somewhere, and you can actually look at what the common start and end times are, as well as heap sizes. Now, the interesting thing about garbage collection is you can still do Erlang GC and sort of compare before and after, but you don't really have the same sort of natural flow point for that. And a lot of those, selecting the right processes to do that on can also be difficult without tracing. So I'm not going to go through all of these, but it goes on, and then it goes into the messages, which I'll show later. So about this, the Beam is really, it's a complicated, evolved piece of code. So when you look into the tracing implementation there, it's somewhat scattered. I mean, most of it's in one place, but it's very low level. It's directly in the line of certain parts of the dispatch mechanism, which is, to be honest, completely dynamic and really, really interesting, but not the best piece of code to read here. I'd recommend opening things like dbg.erl. This file is a built-in app that does different types of debugging utilities. This includes a rudimentary tracer. There are dozens of other tracing libraries in Erlang. I'm definitely not the first. There's 28 years of history, so I think there are at least like 24. Most of them are dead or just deprecated, but there are some great ones, and I'm not going to be able to enumerate all of them. So pardon me if I leave that out. So beyond that, how does tracing even work? How does anything in Erlang even work? It's obviously trade-offs. Like I mentioned earlier, every function call in an Erlang system is somewhat dynamically dispatched. I say somewhat because it's not exactly deciding out of all functions what to run. It's very explicit. But the interesting thing about it is it's used for a number of features. The main thing that you might think of during this is hot code loading. So you need to decide which version you're calling. It's a really interesting capability. You also have a couple other things related to tracing, but the capabilities of of this are definitely because of trade-offs. And if Erlang suddenly started inlining all of this code, it'd be very, very hard to get the same sort of value out of this. So I highly recommend considering, that you pay for this speed, and there's a good reason to use it. So the main API, let's actually dig into this now. So we have trace pattern. Trace pattern is really useful for things like call tracing, so the flow of actual code. Now we have an MFA, module function arguments tuple there, and that is including a match spec and a flag list. The flag list, I guess we can look at that really quick on Dash here. If we go to trace pattern. So that's without the flag list. Okay, so the flag list here we can see trace pattern flag, and then trace pattern flag is global, local, meta with the PID, call count and call time. These are interesting to know exactly where you want to match specific things. But the idea is basically to say, this is the code I'm targeting. But it's not quite enough because you have a second half, and this is the PID set. So you have sort of an overlapping, if you think of it as a Venn diagram, you have a circle that represents your PIDs, and it intersects with this MFA set that you've set to be the thing of interest. So if you say, here I show PID spec can be a specific PID, existing PIDs, or new PIDs, or all PIDs. Usually you don't want to do all PIDs unless it's a very simple MFA that you're calling, but sometimes you need to brute force that. Just don't be surprised if you get tons of messages. Existing is really great. New is probably the most common one outside of a specific PID. That way you don't disturb things that are already in progress or halfway through some process. That way, if you spawn a new PID, let's say you have some sort of request going through the system, you can basically trace it starting with that process. You pass a flag. How basically says, is it on or off? Am I negating these PIDs or am I adding these PIDs? And then the flags, these are all the things I mentioned before. You can pretty much receive any sort of information you'd want to know from a Erlang primitive standpoint. There are a couple of these flags that aren't necessarily things that happen, but data you want to have added or changed as time goes on or as trace events happen. One is timestamp, and we'll get into that a little more. Another one is set on spawn and set on first link. Those basically allow you to slowly grow the set of PIDs that you're interested in based on what happens to the PID. So if a PID starts another process, with that flag, it will automatically follow through. So about the pattern matching. So this MFA isn't necessarily one specific thing. We can be a little more generic than that. So at the top here we have Acme and any function and any sort of arguments. And then we can say Acme print money, and notice that it's print money and then an underscore there. So it could be print money with no arguments. It could be print money with 1,000,000 arguments. It doesn't really matter which print money it is. That's the one that triggers, and it's just that name. We can specify 2, or some simple number where basically it's a count. So we can get a little more precise there. One thing to not do, and I really, really recommend you be careful about this, is never to be too big of a wildcard. If you expand it to all wildcards here, that will trace everything. Well, everything for the processes you have. And if you're not careful, you'll be tracing your tracer. And we'll kind of go into why that is and how that happens. It's a really nasty feedback cycle. Go ahead.
The arguments, is it possible to do some sort of expression that
So you're talking about...
Where they got the 2, you have a specific argument, 2?
Oh, two is not a specific argument. It's an arity in this case. Yeah. Well,
Okay.
this next slide talks about getting a little closer to something specific. So sometimes you want to be able to say, okay, I really want this many arguments, and I want the second argument to be foo, and I want this other one to be a number, or whatever. You know, you can pretty much do anything here that is a function head. So this includes a guard clause, you know, the when and the actual arity and pattern matching that you would have in a function head. So there's a interesting piece of code that you can get out of Erlang from DBG, and this is re-implemented in many ways through many other modules, so it's not that uncommon. So you have this fun2ms, clever little name, that takes a shell function. Now, in this case, it does not allow a different kind of function to be passed, because I don't know how many people have played around with anonymous function representation in Erlang, but there are actually 2 kinds. There's one you define in the shell, and this is compiled to sort of an AST node, and when it's evaluated, it is evaluated as sort of an AST walk. It doesn't actually do any sort of beam compilation. It's slow. You don't tend to want to do things with these kinds of funs if it needs to be performant. But for interactive prodding and those sorts of things, this sort of expression is just fine. What's great about this is it's also just a great little abstract format. So we can look at this, and we can tell Erlang with this MS transform library that we want to take this fun and we want to transform it into a match spec. And so we can look at an example here. So I've got match spec at the top with this function being called. So I've got this function that takes 2 arguments, recipient and 42. So I check that the recipient is the atom me, and the second argument has to be 42 just by regular pattern matching. And then I tell it to return trace. This is kind of basically saying, if this matches, I want you to basically do this thing. Even though we're not actually going to call something return trace, this is sort of a way to flag in the tracer saying this spec needs to actually run this return trace thing. So the match spec that ends up being built from this fun looks something like what's below. It's actually exactly what's below. This would actually run if you did both, because the patterns would match on both. So I would much prefer write the first. It's a little hard to read the second. You have this guard in the middle that equals. That is a little awkward to read. And for Erlang, unless you're a Lisper most of the time, it's out of order. Return trace, you notice that it's not a function call anymore. It's just a result. So the first thing is the captures. Second thing are the guards, the conditions. And then last is what you actually want back from the match. And so this is where Erlang basically says, OK, in this case, if we pass, what I really want is for you to return the trace. So this is a positive match. So now we can use this in our MFA, where match spec is in that arguments position, and it will give us a much, much more precise trace. And this match will execute extremely fast inside of Erlang. It's very much optimized. So another thing to know about tracing is that it's asynchronous. So we called that trace function somewhere. Now, where does tracing information actually go? It goes to that process that you call those things in. So that self basically becomes the recipient of a flow of messages, large flow of messages from all of these traces, all of those PIDs. So you need to make sure that you carefully select this process. You shouldn't be necessarily needing to do other work in this process, because you may get a lot of other messages and fill up your message box. Things that you might receive look like this. There are quite a few more, but these are some interesting ones. Receive, obvious semantics there. It's got the quotes because it's a keyword, but it's an atom just like everything else. Send. I really like this third one, send to non-existing process. I didn't know there was a way to figure out that something was doing that, but this is a great way to find any sort of dead or dumb code you have in a system and sort of audit, oh yeah, okay, I am actually, every time I run this path in the code, I'm doing some useless work. Let's get rid of that. So stuff like that is really nice. Then there's the obvious call. There's return to and return from. Return to is very much related to call. Return from is really useful. Return from allows you to basically take a different stand and say, I don't really care what you're passing in as much as I care about the actual result. You may have something that takes 5 minutes to run or something that's called a bunch of different ways, but you really want to know, are the results that it's returning back all sane or valid, or am I expecting the right things? Return from is another favorite of mine. Spawns, exits, GC, I mentioned, exceptions. Definitely look at the docs there. So timestamps are another thing I mentioned earlier. The timestamps are actually appended to these tuples. And then the trace atom at the beginning becomes trace underscore TS. So you will have to handle different tuples in your tracer if you decide to enable this. The caveat is the timestamps actually cost a lot. And it's not the tracer that pays that cost, it's the tracee, because at the moment that that trace triggers, it has to create a timestamp. It has to actually go find out what time to include and be somewhat accurate about it. Sometimes that's necessary. Sometimes you do need that pretty accurate timer so you can serialize things very accurately. But there's another issue here. This timestamp thing also can cause a lot of slowdown and contention in your tracees. So be very judicious when you use this. Sometimes it might be better to add the timestamp when your tracer receives it rather than force it upon the world every time you want to get some event. So that kind of gives a quick overview of how that works. It's really easy to break these things. I'm going to rush through a little quicker here, but breaking things is usually okay in Erlang, but in this case, if you're touching enough code, and specifically touching enough code in ways where it's covertly, the code isn't designed or written this way, you may actually cause some serious issues. I did mention tracing the tracer. So, if you have this wildcard and you end up running this on the process that the tracer is involved in, you can actually see recursive expansion of this food tracer handle trace call, food tracer, that is wrapped each time this happens and you do stuff, and that just expands bigger and bigger and bigger until you've got giant terms in your tracer. You need to be very, very careful about not allowing this to happen. One of the first ways to do that is be very careful about your pattern matching. Just don't allow anything in. You really usually don't need everything. There are other things this underscore pattern causes as well. Overload is one. So if you ever watch reduction counts, if you ever get process info on different things, you know that things are executing pretty fast. There are a lot of things going on now. Reduction counts don't really mean function invocations anymore, but they are somewhat related, and unless you want hundreds of thousands or millions of messages to be generated, you need to be very conscious about this. Now, you can have 1 million messages in a mailbox, but you're going to have many gigabytes of RAM to support that. And keep in mind that this isn't just the fact that something was called. It is a copy of everything it was called with. That includes the binaries, references to large binaries. You can definitely create some large leaks if you're not careful. Another one is critical paths. Obviously, there is overhead with tracing. You don't want to enable it on something that you know needs to be in a tight loop. Sometimes you want to make sure you're one step back from that or two, and maybe slowly move closer to that critical path rather than start there and realize that, whoops, I just timed everything out and now my users are getting 500s or something like that. Another one that's a little more complicated and unexpected at first, but makes a lot of sense, is a noisy group leader. If you're tracing, you're usually doing something and then sending output somewhere. Now this output, if it's through different types of formatters or I/O calls, goes to the group leader, and then the group leader handles that. The issue with this is you can create a lot of noise on this, and other things may be able to trying to do something important with this group leader. You can basically halt the ability to see interactive output if you're not careful here, or even input. You can crash the ability to say, oh, I want to send this thing to the shell. Well, the group leader already has 10,000 messages to handle before it handles this line input that you just gave it, so it's not going to get there for 5 or 10 minutes, and by then, who knows, your node is down. So the fact that your tracer may be sharing these group leaders is very dangerous. You probably, if you expect a lot of I/O on your tracing, should set a separate group leader and manage that, or do load shedding. We'll go into that as well. So there are a couple tools. There's DBG. This is built into Erlang. It's very easy to use. You just start the app, so DBG start, and then DBG tracer, and then call DBG TP or TPL with the pattern that you want to match, and then you tell it what to print out, what information to print. So all calls, or only calls on these processes, or whatever information you're interested in. It's not the best, but the fact that it's always there makes it, well, unless you really want to strip it out of a release, it's always there. It's nice to just have go-to. Recon is recently grown a tracing module. It's really nice. It's really simple. I really like this one. We'll get into that, into why. TraceEarl's actually really nice. It's got some nice integration with things like dtrace. Dtrace is a little out of scope here in the sense of, I'm not going to talk about system level sort of holistic tracing and the sort of the combination of, what system calls were made between this function call and that function call, and how often am I GCing versus sending these packets out, information like that. Redbug is a common one. I don't recommend it as much. It does have a simpler interface, but it's, the amount of effort required to pull it in, I feel like Recon has more value in terms of other features. So I don't tend to use that one much anymore, but it is there, and it is worth looking at if you're curious. Spyglass I would have recommended, but Recon is caught up on the basic tracing part, and that's what I would have recommended you use. So I'm not really going to recommend that one at this point. So safety, bailing out is difficult if you've overloaded your group leader. So this is one where sometimes you want something that automatically will bail out for you. Recon will do this for you if it exceeds a certain threshold. It's one of the reasons I recommend it. Be sure that whatever sort of tracing you're doing doesn't interact with other people who might be on the system. I know at Cloudit we have multiple people sometimes looking at the same problem at the same time, and you would be surprised how some of these systems interact. You could easily cross paths by sharing DBG at the same time. DBG is a one user library. Likewise with certain parts of Recon, you need to coordinate. I don't know of any library that really does sort of a multi-operator, segregated tracing at the moment. So be careful about that. You don't want to step on each other's toes. So a couple quick advanced things on tracing, and then we'll talk about some discussion points. So distral interactions is a hard problem. When I first tried to look at these issues, the first naive thing I did was, okay, I've got a list of trace events and another list of trace events, and I'll just add these together and start looking at what happened, and maybe try and roughly order them in time. The problem is you don't really have a clear cause and effect unless you have a lot of work to put all of those dots together, and you end up having to trace quite a bit in your system to make sure that, okay, these two functional modules actually are working the way you expect them, but they go through a few hops through some RPC mechanism and a few other things. Making sure those things are linked together is quite difficult. The main way around this is to make sure you have a clear module or place where RPC starts and ends. That way you can efficiently say, I want things that enter in here and exit over here to be connected and joined. Unfortunately, Erlang makes it really easy to just call anything, anywhere. I mean, you just have the message send to whatever end PID, which could be on any node, and that PID could be running any code. You could even, RPC to whatever you want, and that sort of discipline or lack thereof creates a lot of problems for tracing. So this is something you need to design for. State machines is another one. It would probably be better to show in code, so maybe we can talk about this after. It's a little more involved, but it's very similar to what you might see in property-based testing, where you have a sort of model of what you expect states to go through, and so you have a tracer that knows what it's expecting to read and things it needs to react to and what to connect in each state. So let's say you have something that starts up and reads through a bunch of things, finds a set of things it needs to do, sets those aside, goes through each one. You know in each of that process where it is, and then when it's collecting results, and you can basically create a much more coherent output for your tracing information. So I highly recommend building up these things if you have a lot of messages that cover a long lifetime. These are really good for those things you're tracing that may take 5 hours to complete. Let's say you have data moving between two nodes, and a gigabit link is not going to move a terabyte instantly. So you should have something to sort of track that in stages. Property testing, and I don't mean property-based testing. I mean property testing in the sense that you can have an idea of what you expect 2 points to have, and instead of really recording the fact that things happen, you can record whether or not certain properties hold in different combinations of these things, and say, well, I think we're actually not holding up to our invariant here, where when we restart this worker, we expect this UUID to be this, but this thing is sending some other piece of state, and this never matches, so it restarts from a different point. You can do a lot of things like that. These property testing techniques can allow you to reduce a lot of that, so you don't have to store a lot of information. This is really the only way to do long-term tracing, because unless you want to overload your system with a lot of I/O and basically create a database, you may have millions of these points over the course of 24 hours, and really what you want to afford is whether or not certain things held and where the outliers are, and you can keep track of those. So Spyglass itself, quickly on that. So code loaders are a little lacking. This is one part of Spyglass I'll probably actually build upon and focus on as the actual library rather than some of the tracing things, and then rely on Recon for some of the actual system instrumentation. There's not a lot of value in duplicating effort there, so that's one thing I'm going to do. But furthermore, while I've got some state machines and some property checkers for tracers, I would like to create some more generic things, but it's very hard to do that automatically, as I talked about during my earlier prototypes. But I still do want to find a way to build somewhat of a cookbook, either templates or things you can easily use. So what I imagine Spyglass might end up looking like is a system that creates a remote shell that allows you to easily move new modules and code, start tracers, monitor them, tear them down cleanly, make sure it's cleaned up, make sure you're not overloading the system, and making that really, really easy. That way you have a safe way to operate rather than sort of running into the wall saying, okay, I need this information, and then finding out that there are a lot of caveats. So that's the main portion of the slide deck. Do you guys have any immediate questions or discussion? All right, thank you. We can talk more after.